Hi everybody, good morning. This is Arif. We have a beautiful sunny day in Naperville. I will actually go out later. I'll go pick up my son from daycare. But first, I want to finish my studies here. I still have time, and this is my regular study hours. So as you see, even if I have mastered in physics and math topics, I regularly study. And this is a bit of advice I want to give to you today. It is really important to practice regularly. Regardless of how good you are at a specific topic, unless you practice regularly, you lose your abilities, you lose your skills, you lose your knowledge. Okay, this is for sure. So today I'm actually studying physics, a little bit math, and later on today I will actually solve a really beautiful kinematics problem. I'll shoot a video about it. I have been thinking about it for a while, and it's going to be a little bit different than usual because most of you are used to kinematics problems in one dimension with time dependence. Position is given as a function of time, velocity is given as a function of time, or the acceleration can be given as a function of time. Let's suppose acceleration is given as a function of the position. So how would you analyze or solve this system? Using simple kinematics. So this is what I want to show you. And while solving the equations of motion, we will actually introduce phase diagrams. So without actually solving the time dependence of the position or the velocity, we will still be able to tell a lot of stuff about the motion of the system. And at that point, the phase diagrams are going to help us. This is what I want to show you today. Let me wrap this up, then I will go pick up my son from daycare. He's a smart one. He will be a good scientist in the future, I think. And then in the afternoon, I will shoot a video as I promised. Hello everybody. After picking up my son, we took a walk in downtown a little bit, but it got a little bit cold outside. Then we had to come back. So I'm back in my cave, and I would like to a little bit warm up. It was too cold in the afternoon. We will warm up by solving this question. If you are ready, let's get started. The question says, for a 1D system, acceleration is given as a is equal to minus bx plus c, where b and c are both positive constants. So we would like to analyze this system and solve for x of t. And we are given these two initial conditions. So when t is equal to 0, x is equal to 0. When t is equal to 0, velocity is equal to v naught, which is positive. So initially we are moving in the positive x direction. Another thing that we need to note here, I dropped the subscripts x. So in other words, when I say acceleration, I really mean the x component of the acceleration. So when I say velocity, I mean the x component of the velocity. So I just wanted to clear that. Now, the first thing we observe here is this acceleration is a function of position, right? So in general, we are used to seeing acceleration as a function of time or velocity as a function of time, but not acceleration or velocity as a function of the position. So in general, we write v as a function of time, right? But x is a function of time too. Time can also be written as a function of x, right? So in the end, we can write this v as a function of x. If this is the case, acceleration is given as dv over dt. So time rate of change of velocity, right? But if we can write v as a function of x, this is simply dv over dx times dx over dt. So this term here is nothing but the velocity, right? Time rate of change of position. So in the end, acceleration is simply v times dv over dx. Well, this is good to see. Now the time disappeared, right? So you don't have any d over dt terms. So everything is a function of x now. So we can simply write this equation as v times dv over dx is equal to minus bx plus c. Now we can simply integrate it, right? So this is also something Nice. Okay, we will use this equation and solve for v as a function of x. So let's start here. So this simply tells us that v dv is equal to minus bx plus c dx. So when we integrate it, the limits are crucial. So we will use the initial conditions here. So when x is equal to 0, this also corresponds to time is equal to 0, right? So when x is equal to 0, v is equal to v naught actually. So this is 0, this is v naught. So at any v here, so we'll change this to v prime, and this would be x prime. Integration variables. So the final position would be just x. It is easy to calculate now. So v square minus v naught square over 2, it's just the integral of that, is equal to minus b x square over 2 plus c times x. This is good. So we can multiply both sides with 2. This becomes plus 2cx. So I can put all the x's on this side. So v square plus bx square minus 2cx is equal to v naught square. Put this v naught square on the other side. It seems like I can complete the squares here, right? Let me put one more line here. I will use b parentheses here. X square minus 2c over b x is equal to v naught square. Okay. So how can I complete the squares here? Well, this looks like x minus c over b square, right? But what is missing here? C square over b square. So this is simply equal to x minus c over b parentheses square, okay, minus c square over b square. So v square plus b parentheses x minus c over b square is simply equal to v naught square, then plus I will have c square over b. At this point I can equate the denominators here. So this is b over b, right? So this is nothing but b v naught square plus c square over b. So for simplicity, let's define another parameter. So let's define delta is equal to square root of b v naught square plus c square over b. With this new definition of delta, so I assume delta is of course larger than 0, this equation turns into, so I will divide everything by b. So let's divide by b first. So this becomes b squared here. So this term is nothing but the square of delta, right? So v squared over b plus x minus c over b squared is equal to delta square. Okay? So if I divide everything by delta square, this becomes 1. This is over delta square. This is also delta square. So I'll get this equation here. As you see here, this equation is nothing but the equation of an ellipse, right? On v and x space. So if I put v on the vertical axis, okay, so this is my x, this is my v of x. Okay, so if I plot this, I'll get something like that. The equation of an ellipse, right? The center is at x is equal to c over b. So this is c over b and 0, right? So v is 0, x is equal to c over b is the center. Well, on the x-axis, the width of the ellipse is 2 delta, right? So if I look at this point here, this point will correspond to, so let's call it x2, c over b plus delta. So if I look at this point here, which is the other vertex, right? C over B minus delta. So x1 and x2 are given like that. C over B on the x-axis is my center, and this is my ellipse. So I get this ellipse equation, and what can I deduce from that? So what can this tell me about the motion of this system? So as I know, this system is a one-dimensional system, right? So what does it mean? So when x is equal to 0, when t is equal to 0, the system is at x is equal to 0, and it's moving to the right with some velocity v0, right? So at a later time, so x is equal to 0 is here, at a later time it's moving to the right with some other velocity v. This is as a function of x, right? And x2 is a point somewhere here, and x1 is another point somewhere here. By the way, x1 is negative because delta is larger than c over b, right? You can see that. So x1 is negative, x2 is of course positive. C and b are positive constants, as we all remember. So when t is equal to 0, x is equal to 0. So on this diagram, I'm actually here when t is equal to 0, right? So let me use a different color. So this is nothing but v0, right? Okay, as the system moves to the right, because my initial velocity is positive, so it's moving to the right. So x values gets bigger and bigger. Well, it seems like my velocity increases, okay? So I'm actually moving in this direction. Do I really move on this ellipse? No. The system is still moving to the right, to the left. It's a one-dimensional system. So this is called the phase diagram. This actually shows us how v changes with x. Okay, so my v is increasing initially, right? And when I reach c over b, I come over here, I get a maximum value. Okay, but I'm still moving in the positive x direction. Then my velocity tends to decrease, right? Decrease, and velocity becomes 0. And this is the point where I stop. X is equal to x2. Okay? And the question is, what happens after I stop? Okay? We need to understand what's going on here. So in order to get a better feel of that, what we need to do is we need to plot the acceleration graph as a function of x. Okay? So this is my acceleration, and this is my x-axis, okay? A little bit nicer like that. So this is my x1, and this is my x2 points, right? Okay. And this is my c over b. This is good. So when I plot a versus a as a function of x here, at c over b acceleration is 0, right? When x is equal to x1, you can check that acceleration is positive, okay? And it becomes 0 here. Okay, something like this. So this is x is equal to x2. This is x is equal to x1. This is c over b. Okay, very good. So let's go back and see if our claim was correct. So when x is equal to 0, my acceleration is positive. Acceleration is decreasing, but it's still positive. That's why my velocity in the positive direction is increasing. So change in the velocity is positive. That's why this is increasing. So when x is equal to c over b, v reaches its maximum value, and it can no longer increase. Acceleration is 0 here, and afterwards it gets negative values. So I'm still moving in the positive direction, but my velocity decreases. Acceleration is negative, slowing down in the positive direction. This is good. So when I reach here, x is equal to x2, the velocity becomes 0. Okay? So I stop momentarily, but my acceleration at this point is negative. So that's why my velocity starts to get negative values. In other words, I start to move in the negative x direction. So I simply continue this path. And then what happens back here is acceleration becomes 0. So I speed up in the negative direction first. I reach a maximum speed here. Then I keep going on like that. So acceleration becomes positive here. So after I pass this point, my velocity becomes less and less negative. So I'm actually slowing down in the negative direction. Slowing down in the negative direction, and I actually stop at x is equal to x1. So when I stop here, okay, velocity is 0, x is equal to x1, but the acceleration is positive. So that's why my velocity keeps changing, okay, in the positive sense. So the velocity becomes positive, okay, change in velocity is positive here. Momentarily I stop and then the velocity becomes positive. So I simply move like that on this phase diagram, okay? Another thing we observe here is that this motion is bounded, right? So this system moves to the right, it stops at x2, and then it goes back, and then stops at x1. And then it starts to move to the right again, and then it stops here at x is equal to x2, and then it goes back and forth like that. So the motion is bounded in between x1 and x2. You see how much information we got from this phase diagram. So far, we haven't solved anything about x of t, right? But we can still say a lot of stuff about this system. This is the power of physics and the use of phase diagrams, of course. V is a function of x. I hope you all like the idea of phase diagrams. Before we move on, I would like you to see that the shape of the phase diagram has a strong dependence on the values of C, B, and the initial conditions. Okay? For an example, if B was negative, let's say, so in this equation, B would be negative here, okay? Then this will no longer represent an ellipse. Of course, this would be simply a hyperbola, right? Okay? So we would have a totally different phase diagram. Before we move on, I would like you to see that the shape of this phase diagram also strongly depends on the initial conditions, right? So I have V naught here, delta has V naught in it, and I pick this point as my starting point, right? So forth and so forth. So I would expect that the phase diagram would look different if I chose a different set of initial conditions, and this is what I want to show you now. Well, I would like to pick a slightly different initial conditions, okay? And I will like to pick this point C over B. It seems to me a little bit an interesting point because acceleration is 0 at x is equal to C over B. Okay, let's think about it. At t is equal to 0, I place my box at x is equal to C over B, okay? And I give 0 initial speed. So the system is not moving initially. And it's at x is equal to C over B where the acceleration is 0. So there will be no time rate of change of velocity. Okay, this is a little bit strange, right? I put my system at a point with 0 initial speed and there is no change in the speed. Okay, so what does this tell me? Okay, I should have a system which is not moving at all, right? So this is what I would like to see here. So the time dependence would tell me velocity is equal to 0 at all times. And x would be equal to C over B at all times. So this is what I would like to see when I solve that. Let's do that before we move any further. Now we would like to see what happens on the phase space if I chose a different set of initial conditions. So I pick x when t is equal to 0 as C over B, okay, and the initial speed or velocity is 0. So initially I'm not moving. So using the same equation here, so now the limits of integrals will change, right? So I have v prime dv prime. So this is equal to minus b x prime plus c dx. So initially I'm at c over b, but my velocity is 0, right? So finally, I'll be at some point x, my velocity would be v, right? So this gives me v squared over 2, this side. And this side I'll be getting minus b x squared over 2 plus cx minus, so this is the upper limit, right? Minus b, instead of x prime square over 2, I will have c squared over b squared over 2 plus c times x, which is c over b. So v squared over 2 is simply equal to, I will have minus b x squared over 2 plus cx minus, here this cancels this b, okay? So I'll have c squared here, c times c is c squared over b, I'll have 2 and 2 here. So 2c squared minus c squared is just c squared, right? So this will be minus c squared over 2b. Okay? So if I multiply everything with 2, so this is 2, this is 2, this is c, 2c, and this is 2, right? So if I put everything on this side, so I'll have v squared plus, and I'm going to put everything in b parentheses. So b times x squared minus 2c over bx plus c squared over b squared is equal to 0. Okay, so what is that? v squared plus b times x minus c over b squared is equal to 0. So this is my new equation with the new set of initial conditions. So what does this tell me? Well, v squared is positive, x minus c over b squared is positive. So a positive number plus a positive is equal to 0. The only possible solution here is that v must be equal to 0 and x must be equal to c over b. So as I expected, my system will be always at rest at point c over b. And later on we will learn that this point is nothing but the equilibrium point. And on the phase diagram, this will only represent a point, right? So if I want to draw a phase diagram, it will just be a point on the phase diagram. And we also saw that if I change the initial conditions slightly, okay, the motion is bounded. The system moves between x2 and x1, right? With this initial conditions. And I also show that if I place the system at x is equal to c over b with 0 initial speed, the system always stays there. Okay, so this type of points are called equilibrium points, but in this case it is also stable, because if I change the initial conditions slightly, the system moves about this x is equal to c over b point. So it moves back and forth about x is equal to c over b point. Okay? This is a stable equilibrium. We will learn all about these later on my channel. So this was a little bit detour from the original problem. Now we will continue to solve it. Now we are ready to solve for x of t. Earlier we found this equation, and this is how we plotted the phase diagram. Okay? So at any given time t, I will now assume that the system is moving in the positive x direction, and it's at a point x. Then using this equation, what we can write is v squared is equal to, I'll multiply everything with b delta square, so I'll have b delta square minus b times x minus c over b square here. Okay? So if I take b out, so b squared is equal to, in other words, b parentheses. So I'll have delta square minus x minus c over b square, like that. And if I take the square root of both sides, this is b, we know that v is equal to dx over dt. So now using that, we can solve for x as a function of time, right? What we will have is dx over square root of delta square minus It's minus c over b square root is going to be equal to square root of b times dt. So at this point, we're going to take the integrals. So t changes from 0 to t. Let's call it t prime. Integration variable, this is x prime, x prime. Okay. So my x is going to change from 0 to x, because initially my position is 0. Now we need to make a substitution here. What kind of a substitution? Trigonometric substitution. We will call x prime minus c over b is equal to delta, let's say, sine theta. So when we do that, the lower limit becomes theta 1. So this is going to be minus c over b delta is equal to sine theta 1. Okay. The upper limit would be equal to x minus c over b is equal to delta sine theta 2. So this is something we can use for the limits of the integration. So using that, what we can also say is dx prime is equal to delta cosine theta d theta. Okay. So using these, what we can do here is dx prime becomes delta cosine theta d theta. So the limits are now theta 1 and theta 2. Okay. So down here we will have delta square minus delta square sine square theta. So you can pick, so this becomes delta square sine square theta. So you can take delta square out, so it becomes 1. And delta will be 1 over delta here. So this delta is going to cancel this delta. This is good. So it's also easy to see that theta 1 and theta 2 are in between minus pi over 2 and pi over 2. So we are in the fourth and the first quadrants. So this term here becomes absolute value of cosine theta. But cosine theta is positive, okay, for theta values in between minus pi over 2 and pi over 2. So this comes out as cosine theta. So this cancels that. So this integral becomes just theta 2 minus theta 1. The right hand side becomes, it's easy to integrate that, square root of b times t. So theta 2 can be written as theta 1 plus square root of b times t. We know sine theta, we know sine theta 1. So it may be a good idea to take the sine of both sides. So sine theta 2 will be equal to sine theta 1 plus square root of b times t. Let's multiply with delta now. So delta sine theta 2 is nothing but x minus c over b, right? So I can simply write here x minus c over b is equal to delta, parentheses. This is sine theta 1 cosine square root of b times t. Okay, then plus cosine theta 1 sine square root of b times t. In the last part, we got this equation for x. Okay, and theta 1 is defined as that. Okay, so sine theta 1 is equal to minus c over b delta. And delta was defined like this. Okay, so now what we have here is the first term is sine theta 1. So you can write x minus c over b times delta. So sine theta 1 is equal to minus c over b delta. So we have cosine square root of b times t. Then plus, well, this term here, cosine theta 1, is equal to square root of 1 minus sine square theta 1. So we will have the square root of 1 minus sine square theta 1. So this is going to be equal to 1 c square over b square delta square. Okay, times sine square root of b times t. Now we can write x is equal to c over b minus, so delta delta cancels, this is another c over b cosine square root b times t. Then plus, this term is nothing but b square, So square root of b squared delta square minus c square over b squared delta square. Times I have one more delta here. So times delta sine square root b times t. So if I look at here, so b squared delta square minus c square is simply equal to b times v naught square, right? So this is just b times v naught square. So this delta cancels this delta square here. Then I'll have this cancellation here. Okay, so since we have square root here, so this becomes v naught over square root of b. You can simply write this as sine square root b t. We can use a common parenthesis here. So c over b, this becomes 1 minus that. And this is our answer. So this is how we can write x as a function of time t. So if you want to check, this actually satisfies the initial conditions. So when t is equal to 0 here, right, this is 0, this is 1, so x is equal to 0. So let's take the first derivative and see what we will get. So v is going to be equal to, so the derivative of 1 is 0, the derivative of this is minus, right? So you will have minus c over b times minus sine square root b times t times square root of b. So this becomes square root of b here. This minus cancels that minus. Okay, plus v naught times, so this becomes cosine. So I'll get one square root of b here that will cancel that. So this is actually the v, the velocity given as a function of time t. So when we put t is equal to 0, this term is 0, this is 1, so v is equal to v naught. So the initial conditions are satisfied. Now what we will do is we will take some limits and see if these two give us some other equations we already know. So in the end we are able to solve x of t and v of t for this problem with these given initial conditions. Okay, so now we will check some of the limits. Okay, so we will first check, suppose b goes to 0 limit. Before we move on, I would like to remind you that limit when theta goes to 0, sine theta behaves like theta, and the limit when theta goes to 0, cosine theta is something like 1 minus 1/2 theta square. So we will use these two limits to show what these approach when we take b goes to 0 limit. Okay? So x of t, so this will tend to this limit, so c over b parentheses, so this is 1 minus, the second term would be, it's a cosine function, so 1, this minus becomes like 1 plus 1/2, the square of that, say b t squared. Okay, and plus this term would be v naught over square root of b times square root of b times t. Okay, so x of t will tend to, so 1 cancel. Okay, so we have b here and another b here, so this becomes 1/2 c t square, okay, plus v naught times t. Is this something we would expect? Okay, 1/2 ct square plus v naught times t. Yes. Okay, when we take b to be 0, acceleration is constant, and this is one of the kinematics equations we have for constant acceleration, right? So c is our acceleration, 1/2 acceleration t squared plus initial velocity times time, right? So this gives us the displacement. Since initial position is 0, x simply gives us the displacement. And this is what we know from kinematics for systems with constant acceleration. So what does v give us? So v of t goes to, so let's check that. So this is c over square root of b times square root of b times t plus, so this will simply give us v naught. Okay? So this cancels that, and as we would expect, v of t goes to ct plus v naught. So the initial velocity plus acceleration times time. Right? So if b goes to 0, this is nothing but a one-dimensional motion with constant acceleration. Okay, so now we will check the other limit. Well, checking this limit is easy. So when c goes to 0, x of t simply goes to, so this term would be 0. So v naught over square root of b sine square root of b times t. That's it. And v of t will go to, so c, this term would be 0, v naught cosine square root b times t. So when c is 0, so a is given as minus b times x and b is positive here. So later on we will see that this is nothing but a simple harmonic oscillation. So this is also simple harmonic oscillation with its equilibrium point a little bit shifted due to the term c. So we will discuss all these problems later on this channel. I hope you liked how we solved this problem and the concept of phase diagrams. This is all for today. See you next time. Bye.